I'm Alan Over.
And I'm Fletcher Turner.
And we are the FM Transmitter Group. Our purpose is to build a working FM transmitter that can be picked up by a standard radio receiver. Additionally, it's to learn about the theory behind it, not only of the circuit, but also of FM signals in general, in comparison especially to AM signals. And finally, to analyze the circuit with a spectrum analyzer and oscilloscope. And this means gaining experience with the new device, the spectrum analyzer. So let's take a look at signal modulation types. The three types primarily are pulse modulation, or PM, amplitude modulation, or AM, and frequency modulation, or FM. First, pulse modulation has a waveform that looks like this. And it essentially encodes information by directly turning the signal off and on. This is commonly used for Morse code transmission, as well as radio-controlled clocks. But other than that, it's relatively uncommon. So on to amplitude modulation. In this case, amplitude is encoded in the amplitude of the signal, as you can see here. This is normally just used for AM radio stations and the picture portion of a TV signal, and operates in 540 to 1600 kilohertz range. And finally, and the most important for this project, is frequency modulation. In this case, the information is encoded by changing the frequency of the signal, as you can see in this diagram here. This is commonly used in FM radio stations, the sound portion of the TV signal, and even in cell phone signals. It operates in the 88 to 108 megahertz range, and it normally has a higher quality sound due to the way it's encoded. Basically, in amplitude modulation, or AM, any changes in the amplitude result in static. In FM, that doesn't necessarily matter because the information is encoded in frequency, and so the amplitude is basically irrelevant to the information.
So we're going to talk about the differences between the audio and the carrier waves frequencies. So the first frequency you see right here is the actual audio out of whatever you have connected to the FM transmitter that's actually generating the music or sound that will be received. Then we have the carrier wave, which is actually what you tune into on an FM receiver, and that's what carries the audio wave, which produces the FM signal that actually modulates the frequency, changes up and down, and your FM receiver interprets that as the audio that was sent out on the carrier wave.
Spectrum analyzers show the magnitude of a signal versus the frequency. We'll use it to find the frequency that our transmitter puts out by looking to see where there's a large spike in the magnitude of the signal. Where the spike occurs is the frequency output of the transmitter. We need to use a spectrum analyzer specifically because it has a very large range of frequency that'll definitely show the signal. Subsystem 1 acts as a bandpass filter using the electrolytic capacitor in the first 0.01 microfarad capacitor. The impedance of a capacitor is inversely related to the frequency, so when there is very high frequency, the impedance is very low, so both capacitors will act as a short, letting the current flow to ground through the 0.01 microfarad capacitor. This prevents the signal from reaching the rest of the circuit. When the frequency is very low, the impedance is very high, which causes the capacitors to act as an open circuit, also preventing the flow of the signal. This bandpass filter keeps the frequency in an acceptable range for the rest of the circuit.
Subsystem 2 serves many purposes. First, the inductor and capacitor form an LC tank as part of a modified Colpitts oscillator. In the LC tank, the two components alternate charging up the other, dissipating, and charging the other up again. In theory, this exchange would last indefinitely, but due to the inherent impedance in these components, energy is lost over time. The transistor acts as a switch, opening and closing at the correct frequency to allow energy to be returned to the system. The resonant frequency of the inductor and capacitor determines and generates the carrier frequency of the transmitter. The transistor's parasitic capacitance is also utilized, which changes over time due to the audio in signal. This relationship forms the modulating frequency, which modulates the carrier frequency to generate the broadcasted FM signal to be received elsewhere.
Subsystem 3 primarily serves two major functions in the overall circuit. First, the two capacitors on the right act to filter out any DC offset before the signal is transmitted via the antenna. Second, the transistor acts as an amplifier to the signal, as a gain is applied to the base current. This gain is the beta, or HFE, which is based on the collector current and can be found from the transistor's datasheet. The base current is multiplied by the gain to result in the value of the collector current.
The equation on the left is used to calculate the frequency at which the transmitter broadcasts, where L is the inductance of the coil and C is the capacitance of the capacitor associated with the output. The inductance is calculated with the equation on the right, where N represents the number of turns, mu naught is the permeability of free space, A is the cross-sectional area of the coil, and L is its length.
The antenna is an optional feature of the circuit designed to boost the signal output. It's shown in our circuit as the yellow wire coming from the pad.
The materials used to construct the FM transmitter are the FM radio receiver, which is used to test the finished product, a NPN2N3904 transistor, a battery clip, a phone plug, 22 gauge copper wire, which is multicolored, and you mostly need red and black, but it's helpful to have other colors as well. 2.1 microfarad capacitors, two 10 picofarad capacitors, one 9-volt battery, 18 gauge solid copper wire, which is used to construct the inductor, a 470 ohm resistor, one 10K ohm resistor, and one 27K ohm resistor, and also a copper board, which is used as a breadboard, and a 22 microfarad electrolytic capacitor. And some extra materials that are used just for construction are a utility knife, crazy glue to glue down some pads on the copper board, solder, and a soldering iron, as well as some wire cutters and wire strippers. We built this circuit according to the schematic shown earlier using step-by-step instructions posted online by Make. We used the copper board instead of a breadboard because breadboards have too much noise at high frequencies. Cut the board to a reasonable size and cut out 5 small pads, gluing them on using the crazy glue as is shown. All connections will be made using soldering. The first pad should have one end of the inductor and each of the 10 picofarad capacitors connected as well as the collector of the transistor. The second pad should have one end of the inductor, 27K ohm resistor, and 0.01 microfarad capacitor attached to it, as well as the positive lead of the battery clip. The third pad should have the positive end of the electrolytic capacitor, one end of the 10K ohm resistor, and the 27K ohm resistor, and the 10 microfarad capacitor, as well as the base of the transistor connected to it. The other ends of the 10K ohm resistor and the 10 microfarad capacitor should be connected to the ground as shown. The fourth pad should have the negative lead of the electrolytic capacitor and the positive lead of the phone plug connected to it, with the other lead connected to ground. The fifth pad is connected to the emitter of the transistor and the other end of the 10 picofarad capacitor, one end of the 470 ohm resistor, with the other end being connected to ground and the antenna. After this, trim any loose or extra wires and test the circuit to ensure that it works.
This is a screenshot of the potential measured at the output of the antenna of the transmitter. Here, the frequency modulation can be seen as the wave's period shortens and lengthens. Now, let's zoom in. Unfortunately, this doesn't tell us much because this is above the range of the oscilloscope, so we have to use the specialized spectrum analyzer. This is a screenshot of the spectrum analyzer measuring the frequency of the transmitter when no audio in is provided. The peak is our broadcast frequency. This video shows the carrier frequency being modulated while music is being transmitted. We faced a few complications in this circuit project. The first construction of this circuit did not function correctly as we believe we used an incorrect resistor value in the initial build. Poor soldering may have also resulted in the initial failure as we may have neglected to properly strip the varnish off of the copper wire that formed the inductor.
For future improvement, we would likely begin by using an expanded version of the circuit, as this version repeatedly relies on the same components for many different functions. An expanded version would separate these functions, allowing for easier analysis and troubleshooting. Additionally, we would likely use a pre-built inductor if possible for better frequency selection. Finally, we would create a more appropriately sized antenna by calculating the wavelength based on the frequency.
So this was our FM transmitter.
Thank you for watching.